Welcome back. This is Chapter 5, Video 1, in which we'll be discussing the basics of the language P. In Chapters 2 through 4, we had been using the language S. This was a language which takes whole sentences as the basic unit, and those are joined or modified by the truth functional symbols, and this allowed us to focus on truth functional logic. There's some shortcomings of the language S. First of all, it doesn't show the internal structure of simple sentences. The only structure it can show is the truth functional structure of whole sentences combined. Moreover, it cannot handle quantity terms, all, some, none, and various others, except in a very limited way. As a result, it cannot handle quantificational logic. So what we want is a new language, which we'll call P. It will be an expansion of the language S. It keeps the whole sentences and truth functional connectives, but adds predicates and terms to show the internal structure of sentences. And predicates will be the basic unit now. In addition, it adds quantifiers and variables so that we're able to handle quantificational logic. Quantificational logic is just the logic of sentences involving quantifiers, predicates, and names. Now, in order to deal with quantity terms like all, some, and none, we need to add quantifiers to our language. Quantifiers consist of a quantifier symbol and a variable, and then the variables will also be used in the predicates. So what are the quantifier symbols? We have an upside down A as our universal quantifier symbol, and an upside down E as our existential quantifier symbol. We will also have the variables v, w, x, y, and z with or without subscripts if we need more than just the 5. These are lowercase letters like our constants, but our constants will always come from the beginning of the alphabet, A through U, and our variables come from the end of the alphabet, V, W, X, Y, and Z. Now when we put the quantifier symbols together with a variable and enclose it in parentheses, we get the actual quantifiers. So for example, upside down AX in parentheses, or upside down AZ in parentheses, these are universal quantifiers. And if we use the existential quantifier symbol, upside down EX or upside down EW, say, then we've got existential quantifiers. When we form these quantifier symbols, we only ever have one upside down A with one variable, or one upside down E with one variable. And we enclose them in parentheses. Some books you might have seen don't use parentheses around their quantifier symbols. That's just a stylistic choice. We will use them. So what do these quantifiers mean? Well, for the time being, let's stick with the variable x. So if we have a universal x quantifier with some phrase after it that's also going to contain a matching x variable, we could read this as for all x, something about that x, or more officially, for every x in the universe of discourse, something about that x, or more simply, all x, something about that x. We'll fill in those dot dot dots in a little bit with the use of our predicate letters, so when we start doing actual translations. Similarly, for the existential, we have for some x, something about that x. And by some, what we mean is at least one. So we should always think of some here as there exists at least one x in the universe of discourse such that that x something something. We'll fill in those blanks later. And here you can see why it's called the existential quantifier, because with that upside down e, we actually assert the existence of at least one thing. With these two quantifier symbols, the universal and the existential, we'll be able to produce various sorts of quantity claims. And in fact, with a little bit of help later on in the chapter, we can make just about any sort of quantity claim we want. Let's see how it works in practice. I've moved the interpretation up into the corner a little bit so we have more room. Let's see what some basic quantificational claims look like. Suppose we wanted to say that all the cats at the kennel are striped. Since we specified in our universe of discourse that we're talking about the cats just at this kennel, I'm going to drop reference to the kennel, and we're going to say in English. Now we know, since we have an all here, we're going to want to use a universal quantifier. So let's set that up. For all x, well, what do we want to say about those x's? We basically just want to say that they're striped. Well, we'll use the one place s predicate. But instead of filling in that blank with one of these particular constants to name a particular cat, we're instead going to fill that blank in with a variable. Now that variable needs to match the one we used in the quantifier, so we'll put x in there. So reading it symbolically, what we have is for every x, sx. Given our interpretation, that means that all the cats in the kennel are striped, or every cat in the kennel is striped. Pretty straightforward. Suppose we wanted to say some cat is striped. Well, it's exactly the same thing except with the existential quantifier. We take existential x and pair it with sx. So this means that there is at least one object in the universe of discourse x such that sx, at least one object in the universe of discourse x such that x is striped. And since our universe of discourse are the cats at the kennel, that means that at least one cat is striped. Some cat is striped. It could be more than one cat. It could even be all the cats, but it's at least one. Now we also talked about none as a quantifier. So we should be able to say none of the cats is striped, or equivalently, no cats. Now this we can do in two pretty obvious ways. If no cats are striped, then it's not the case that there exists a striped cat. So we can take there exists a striped cat and negate it. Similarly, if no cats are striped, we can say that all the cats are non-striped. Notice with this one, we've got a universal quantifier, and we're saying of everything that it is not striped. So we can squeeze a negation right in there on the predicate letter and then put the quantifier on the left-hand side of it. Similarly, if we take this sentence here and stick a hook on it, we wind up with this. So negations, just as always, can be stuck onto the left-hand side of complete units to negate them. Let's see one last example in this group. Some cats are not striped. This is similar to the one above, but the negation is going to be differently located. We can write there's at least one x such that x is not striped, and we get some cats are not striped. We can also do a version with the universal quantifier where we say, well, think about it. If some cats are not striped, then it's the case that not every x is such that x is striped. So what we have here are four corners of a square. And you notice that on the right-hand side, in each case we have an option which is the direct negation of one of the translations on the right-hand side. What this is telling us is that the opposite corners in this square are contradictories. That means that we also have an alternate translation for all cats are striped in the upper left corner, which takes one of the translations from the lower right corner, this one here, we're going to move it up there and stick a hook on it, and since the corners are contradictory, sticking that hook on it will create equivalence. That is, another way to say all cats are striped is to say it's not the case that there exists an X which is not striped. Similarly, with the lower right corner, some cat is striped, and this right here, if we move it over and stick a hook on it, we will get an equivalent formulation. That is to say, one way to say some cats are striped is to say it's not the case that all are not striped. We've got 4 basic quantity terms here: all, some, none, and some not. And the pair in each corner is an adequate translation of that quantifier. The previous set of translations are instances of what we'll call the simple square of opposition. These are the 4 simplest quantificational forms, and a lot of what we will do builds off of these. In the upper left corner, you have your everything is F, or all X FX. The instance we had was all the cats are striped. Below that, we have the basic existential form something is F, some X FX. And at the top right, we had the none, no, or nothing is F, no cats are striped. And we saw 2 convenient ways of symbolizing that. For all X, not FX, or it's not the case that there exists an X such that FX. It's not the case that there exists a cat that is striped. And directly below that, we have the something is not, which is most intuitively translated with an existential and a negated predicate, but can also be done as not all. Furthermore, we saw that the diagonally opposite corners are contradictories. They're saying the exact opposite. For example, if the form up in this corner is true, everything is F, then it must be false that something is not F, and vice versa. Similarly, if something, at least one thing, is F, if at least one cat is striped, if that is true, then in the upper right corner, nothing is F, no cat is striped, must be false, and vice versa. So the diagonally opposite corners always have opposite truth values. There are a few other interrelationships we can check out on this square as well. For example, the top corners imply the corner directly beneath them. If everything is F, then at least one thing must be F. If all the cats are striped, then there's at least one striped cat. Similarly, if none of the cats are striped, then there's at least one cat that is not striped. Nothing is F implies that there is something that is not F. There are also these horizontal relationships, which are a little bit more tricky, but not too tough. So for example, across the top, it cannot be the case that both those top corners are true. If everything is F is true, then it must be false that nothing is F. But it's also the case that if nothing is F is true, then it must be false that everything is F. So they cannot both be true. However, they can both be false. Suppose some things are F, making this one false, and some things are not F, making this one false. That is, if some things are and some things aren't, both top corners will be false. So we call that the contrary relationship. They can't both be true, but they can both be false. It's a little different than contradictories. And below that, we have the subcontrary relationship. The two bottom corners can't both be false at the same time. If it's false that something is f, then it must be true that something is not, and vice versa. If it's false that something is not f, then something must be f. But they can both be true. You can have some things are f and some things are not, as when we have some cats that are striped and some cats that are not. So on this square of opposition are the four most basic quantificational forms upon which many other translations will be built. We'll see a more complicated square in the categorical square of opposition later on. But this is a good place to start. Note, you don't really have to remember all of these relationships. In fact, if you just remember the contradictories and the downward implications there, you can reproduce the subcontrary and contrary relationships. One additional point worth noting here is that if we focus on the upper left and lower left corners of this square, we can see the quantifier equivalences. What we mean by this is that for any given predicate fx, all x fx is going to be equivalent to replacing the universal quantifier with the existential quantifier flanked by negations, not some x, not fx. And in the corner below that, we see that a syntactically similar equivalence applies. Some x fx is equivalent to a universal quantifier flanked by negations. If you read this through, what we've got here is that for all x fx is equivalent to, it's not the case that there exists an x that is not f. If it's not the case that there exists one that's not, then they must all be f. Similarly, there is at least one x such that fx is equivalent to, it's not the case that every x is not f. If it's not the case that every one of them is not, at least one of them must be f. We can also display this pattern in the following way. If we have a negated universal x, fx, that is equivalent to existential x, not fx. There must be at least one thing that is not f. And in parallel, if there does not exist an x that's f, that is equivalent to saying all x not fx. And that actually is the right-hand side of the square of opposition we've just been looking at. That is to say, each of these equivalences corresponds to the equivalence in one of the corners of the square of opposition. So as you might have guessed, we could actually do away with one of those two quantifiers. We could get rid of the existential and only ever use the universal, or get rid of the universal and only ever use the existential. But here again, we have both because it makes saying most things easier to have an option of which to use. Because obviously it would be kind of annoying to always have to write negation, existential negation when we wanted to write universal, or to write negation, universal negation when we wanted to write an existential. So having both symbols creates greater ease of expression. Knowing these equivalences, whether you understand them in terms of the square or just the positioning of the negations, will be helpful in doing exercises. So this video has introduced you to some of the basics of the language P, how predicates and constants work, how quantifiers and variables work, at least in their basic sense, and some basic translation forms. The next video will discuss how the quantifiers interact with conjunction and disjunction.